All right, so today we're going to work on 3.4, which is rational functions and their graphs. So let's take a look. So here are some examples of some rational functions. When we have 1 over x, which we know is the parent function. We've talked about this when we did translations. And then we proceed from there to see how the graph changes based off of different types of changes, right? And we see that the graph can change several ways, right? We have x squared. We have x squared plus x minus 2 with x minus 3 on the top. You know, we have this whole possibility that's going on here. So we're going to learn how we can graph these rational functions. So rational functions are functions of the form where we have g of x over h of x. So we have two distinct functions being divided by each other, right? So to find the domain, before you factor, you set the denominator equal to 0 and solve for x, and exclude these x values from your domain. So what we're saying here is in our domain, we're going to look at just our bottom form here. So we have x squared plus 5x plus 6 here equals 0. So if we solve this, we need to factor. We get x plus 2 times x plus 3. So then x plus 2 equals 0, x plus 3 equals 0. So x equals negative 2 and x equals 3, negative 3. We know that those cannot be solutions because our denominator cannot be 0. So our domain is everything but those values. So from negative infinity to negative 3, union negative 3 to negative 2, union negative 2 to positive infinity. So that's our domain. All right, so find the x-intercepts after you factor and cancel the set numerators for 0 and solve for x. So we can do this by first factoring and canceling. So we just factored this on part 1. So we know that factored to x plus 2, x minus 3. So now we need to factor the numerator. So the numerator here is going to be x and x. We're going to have a minus plus, and it's going to be 3 on the negative and 1 on the positive. So then this x minus 3 on top and bottom cancel, and we get x plus 1 over x plus 2. Now that we have that, we want to set the numerator of our factored form equal to 0. So we're going to say, okay, x plus 1 equals 0. And we're going to solve. So x equals negative 1. So our x-intercept is the point negative 1, 0. All right, so step 3 when we are graphing these functions is to find the y-intercept. So we've already, with the y-intercept, you know you're just substituting in 0. So when you put a 0 in here, this whole term is going to go to 0. This is going to go to 0. That's going to go to 0. That's going to go to 0. And you're just going to be left with this back part here. So negative 3 over 6, which equals negative 1/2. So our y-intercept is the point 0, negative 1/2. So the next step is talking about asymptotes. So remember, asymptotes are those imaginary lines that we draw with a dotted line where you can come all the way up to them, but you cannot actually touch them, right? So we want to first find vertical asymptotes. So after you factor and cancel the set denominator, then you can go from there. So we've already factored this one, canceled everything, and we got to the point x plus 1 over x plus 2. So the vertical asymptote is that x plus 2 portion set equal to 0 and solved. So x cannot be equal to negative 2. So there's an asymptote at the line x equals 2 or negative 2. I'm just going to rewrite this. I keep messing up. Give me just a second. So that was 0, x equals negative 2. So x equals negative 2 is where the asymptote is. Okay, so there. So then the fifth step, we can find horizontal asymptote or determine if there is not a horizontal asymptote. So we do that by comparing the degree of the denominator and the numerator. So on this problem that we've continued to work, the degrees here are the same. Okay, so that means that we would have y is equal to 1 because the degrees are the same. Okay, because we have the leading coefficient, right? So actually, if you thought this out, the leading coefficients here is 1. The leading coefficient, if you look here, is 1 and 1. So that's where that y equals 1 comes from. So y equals 1 is a horizontal asymptote. So the last is if there's an oblique asymptote. You only have an oblique asymptote if you do not have a horizontal asymptote. So if the numerator's degree is greater than the denominator's degree. We see that when we looked back here, this is when you don't have a horizontal asymptote. We have a horizontal asymptote, so we don't need to worry about this. We have no horizontal asymptote because 2 equals 2. So 2 is not greater than 2, right? It's the same degree. So that tells us all of our pieces. So let's work a few where we do all the pieces as we go. So first we're going to look at this, determine the vertical asymptote of the graph of the function. So we only want the vertical asymptote here. So if we look at our rules for vertical asymptotes, we are just comparing those. For vertical asymptote, first we have to factor everywhere we can, cancel what we can, and then look at the denominator that's left over. So first we're going to pull out an x squared here, an x here, because every term has an x, right? X, x, x. So for our denominator, if we pull out an x, we are left with 2x squared minus x minus 36. So now we can factor that. We have 2x minus 9 times x plus 4. Now we also can cancel where we see. We have an x to the 1 here and an x cubed here. So this x will cancel and this will become x squared. So we end up with x squared over the factored portion that we have down here, 2x minus 9 times x plus 4. So then we have to set the denominator equal to 0. So both pieces are going to be equal to 0 and solve. So x is 9/2 and x is negative 4. So we have vertical asymptotes at both x equals 9/2 and x equals -4. This one says, determine the horizontal asymptotes of each function. So our horizontal asymptote is where we're comparing those degrees. So we have 2 and 4. So the numerator is less than the denominator. So if we go back to our rules where the numerator is less than a denominator, y equals 0. Okay. So here, your horizontal asymptote is y equals 0. So then on this one, they're the same. Okay, numerator equals denominator here as far as the degrees go. So it is the coefficients. So we're looking here, the coefficients of the leading term is 2/3. So there is a horizontal asymptote at y equals 2/3. Okay. We want to find the oblique or slant asymptote. So we know that we will have one here because when we look at this degree here, 2 is greater than 1. The numerator is greater than the denominator. So to find this one, we're going to look at a special way to find this. We can use that division that we've been talking about this whole time in the previous lecture. So the top is my dividend, right? X squared minus 5. And we're dividing by x plus 4. We have to remember that when we do that, we have to fill in our 0 terms, right? So we're missing a linear term, so 0x minus 5. So this is what we're actually going to have to divide. So now we are just going to do division like we learned in the last lesson. To get x squared, I need to multiply by x. So then I get x squared plus 4x, and that's being subtracted. So I get negative 4x. Bring down my minus 5. To make x a negative 4x, I multiply by negative 4. Negative 4, x, and then minus 16. We're subtracting here. So we end up with positive 11 because that negative will make that positive. So positive 11 here. So your slant asymptote is whatever you get here. So y equals x minus 4 is our slant asymptote. So whatever you get for the quotient here, regardless of the remainder. All right. So let's tie this all together in a problem. So first we need to find the domain. Remember, domain, you set the bottom equal to 0 and you solve. So x is equal to negative 2 cannot happen. Here, let me write this by the domain so we remember. So we know for domain, x plus 2 being equal to 0, we can't have division by 0, so x cannot equal negative 2. So that means our domain is going to be from negative infinity all the way up to negative 2, union negative 2, all the way to infinity. So then for the x-intercepts, we have to take the numerator. So here we did the denominator for the first step. The next step, we have to factor the numerator. So when I factor the numerator here, I get x squared minus 6x plus 8 factors 2x minus 4 and 2. So then I set those equal to 0. And so I get x equals 4 and x equals 2. So our x-intercepts are 4, 0 and 2, 0. So then the y-intercepts, remember the y-intercepts come from the point that if you have, let's just take our factored, let's just look at if we have x squared minus 6x plus 8 over x plus 2. These terms will zero out and we'll be left with 8 over 2, which is 4. So our y-intercept is 0, 4. So our vertical asymptote, again, comes from that denominator, x plus 2 equals 0. So x equals negative 2 is where we have a vertical asymptote. Let me write it beside it so it doesn't get in the way of the horizontal asymptote. So x equals negative 2 is our vertical asymptote. Now, horizontal and oblique, again, you're only going to have one or the other. So we're going to look at our degrees here. So we have our leading term is x squared over x. So the numerator degree is bigger than the denominator. So there is no horizontal asymptote, which means there has to be an oblique asymptote. So I'm going to do my long division over here for my oblique asymptote. So x squared minus 6x plus 8 divided by x plus 2. So that would be x there to give me x squared minus 2x. So that becomes plus a positive here. So that's negative 4x. Bring down our 8. So we would need multiply negative 4. And then from there, it wouldn't matter, right? Because all we care about is this here, right? So our oblique asymptote is at y equals x minus 4. Let's do another one. So here, again, for your domain, the first thing you're going to do is factor here. So this is one of our special types. It's x plus 3, x minus 3. So we know that x cannot equal negative 3 or 3. So our domain is from negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. So x-intercepts now. Because our numerator is a constant, okay, our numerator is a constant, there is no x-intercept. Okay. Y-intercept still comes from letting those terms equal 0, right? So if I have 4 over 0 squared minus 9, I'm ending up with negative 4/9. So my y-intercept is the point 0, negative 4/9. Vertical asymptote, because we solved up here, we know that we have vertical asymptotes at x equals negative 3 and x equals 3. And our y, because we don't have an x on the top, we have a constant. That means that our power, the higher power is in the denominator. So the numerator is less than the denominator. Let me write it here. We have 4 over x squared minus 9. There is a 0x up here to the 0 power. And so 0 is less than 2. So since n is less than d, our numerator less than our denominator, that means that our horizontal asymptote is y equals 0 according to our rules. which means there's no oblique asymptote. So it's really a quick and easy process once you understand how to do each piece. So make sure you fully understand each piece. So the whole point is so we can graph. So let's find the right graph by doing this for this one. So our domain for this one comes from the fact that x plus 3 cannot equal 0, which tells us that x cannot equal negative 3. So since x cannot equal negative 3, our domain is from negative infinity to negative 3, union negative 3 to positive infinity. Okay, so that's the first thing we need to check. Is our graph got a negative 3? Like, where is that at? Okay, so then let's go ahead and do the x-intercept. The x-intercept here would be the numerator solved. So the x-intercept is the point 6, 0. So the y-intercept comes from taking those zeros out. So we get negative 6 over 3. So that becomes negative 2. So our y-intercept is at the point 0, negative 2. So we know we have vertical asymptotes at that x equal negative 3. Okay, so let's just see where we're at so far. We know that x equals negative 3 has to have a vertical asymptote. Well, this vertical asymptote is on the wrong side. So is that. So it's either this one or this one for the vertical asymptote. Then we have a y-intercept at negative 2. This one doesn't have a y-intercept at negative 2. And we have an x-intercept at 6. So 2, 4, 6. 2, 4, 6. So this one is missing the point we need. So it's this second one that is our solution. Let's go look at another. So here, first, we know that our domain, x plus 2 cannot equal 0, so x cannot equal negative 2. So our domain is negative infinity to negative 2, union negative 2 to infinity. This also tells us that we have a vertical asymptote at x equals negative 2. Then we have x plus 4 times x minus 4 for our numerator. So for the x-intercepts, we have x plus 4 equal to 0, x minus 4 equal to 0. So we have x-intercepts at negative 4 and positive 4. So we're going to have the points on our graph negative 4, 0 and 4, 0. Then the y-intercept we can think about. So we would have negative 16 over 2 when we take those 0 out, so negative 8. So we should have a point at 0, negative 8. So just knowing that, finally we can decide whether we have a vertical or slant. All of ours has a slant, so let's just skip that step and go from here. So we have points. Well, first we know we have an asymptote at negative 2. So this one's out and this one's out. So then we have points at negative 4, 0, 4, 0, and 0, negative 8. So we have points at negative 4. This is hard to tell. Okay, this is factors of 10. So it would be 2, 4, negative 4, 0, 2, 4, negative 4, 0, 2, 4, 4, 0, 2, 4, 4, 0. And then -8. And so this one has the asymptote. That's not going to let it cross -8. But this one over here on this side will cross at -8 right there. So this is our solution. And so that concludes 3.4, which is the last in Chapter 3. So you should be able to start working your review and preparing for your exam.